My name is Bruno Reisman, and I'd like to give an update on Rift Python, which is the open source implementation of Rift. Since the IETF 105, which is when I gave my most recent presentation, we've added the following features to Rift Python. Number 1, negative disaggregation, which is needed to deal with certain failure scenarios in multiplane topologies. That feature was actually implemented by Mariano and Tommaso from Roma University. 2, fabric bandwidth balancing, which spreads the traffic evenly across multiple parallel links according to the available bandwidth. And 3, performance monitoring, which helps us discover bottlenecks in the code. Let's dive right in and start with multiplane topologies. Up until now, Rift Python only supported single plane topologies, such as the one shown in this diagram. In a single plane topology, every superspine node is connected to every spine node. As a result of this, the superspine nodes quickly run out of ports. To deal with the limited number of ports on the superspine nodes, we introduced the concept of multiple planes, such as the blue plane, the red plane, and the green plane in this example. The superspine nodes in each plane are connected to a corresponding subset of spine nodes in each pod. In order to make negative disaggregation work, we also need so-called east-west interplane loops that interconnect the superspine nodes in the different planes to each other. These east-west top-of-fabric links are only used to carry control plane traffic and not user plane traffic, and for that reason they can be low-speed links. Rift Python includes a configuration generation tool that takes a very high-level description of the topology, the so-called meta topology, as input and generates detailed configurations for individual Rift nodes as output. This tool has been enhanced with the ability to support multiple planes. Here we see an example of a multiplane topology generated by the configuration tool. In this example, we have 3 pods, and we have 3 planes, and we have east-west interplane loops to connect the planes to each other. In these multiplane topologies, there are new failure scenarios that can be fixed with negative disaggregation. Before I get into the details of negative disaggregation, let me first say a few words about disaggregation and Rift in general. One of the defining features of Rift is that it uses a default route for northbound traffic. That default route works fine as long as there are no failures anywhere in the topology. But if there is a failure in the topology, it's no longer possible to use a default route for all northbound traffic, and it becomes necessary to install more specific routes for certain prefixes to route the traffic around the failures in the network. This is exactly what disaggregation in Rift is. It's the installation of more specific routes to route the traffic around failures in the network, and to do that in a fully automated way. There's actually 2 types of disaggregation in Rift. One is called positive disaggregation, and this type of disaggregation deals with most types of failures in the network. Positive disaggregation was already implemented in Rift Python some time ago, and I described it in detail in my presentation at the IETF 105. What I'm going to talk about today is the other type of disaggregation, which is called negative disaggregation. It works in addition to positive disaggregation to deal with one specific type of failure that only happens in multiplane topologies. Even though you don't need negative disaggregation in single plane topologies, it is still one of the most interesting and most novel parts of Rift, and I hope and I expect that it will have an influence on the design of other routing protocols as well. In order to understand the concept of negative disaggregation in Rift, you first need to understand the concept of negative prefix advertisements. All routing protocols up until now have used what Rift would call a positive prefix advertisement. When a routing protocol advertises a prefix, it is saying, I know how to reach that prefix. If you have any traffic to send to that particular prefix, you can send it to me and I will get it to its final destination. So in other words, a positive prefix advertisement is used to attract traffic for a certain prefix. If there are multiple routers advertising the same prefix, then the rule is that the most specific advertisement, the one with the longest prefix match, wins. This concept of using the longest prefix match is supported in current generation hardware. Rift introduces a new concept, namely the concept of a negative prefix advertisement. When a Rift router negatively advertises a prefix, what it's saying is, I don't know how to get to that prefix. If you have any traffic to send to that particular prefix, you better not give it to me. In other words, a negative prefix advertisement is used to repel traffic for that particular prefix. A router that receives one of these negative prefix advertisements is supposed to use any other available route to get the traffic to its destination, even if that other alternative route is less specific. One thing to keep in mind is that a negative prefix advertisement is a control plane concept only. Just before Rift installs these routes in the forwarding plane, it translates negative next hops into positive next hops, and we'll see the details of how that actually works in one of the later slides. This slide shows the type of failure that negative disaggregation was designed to fix. In this slide, we have a topology with 3 pods and 3 planes. Pod 1 is completely disconnected from plane 1 because both of the links that connect pod 1 to plane 1 have failed. Pod 1 is still connected to plane 2 and plane 3, but it's disconnected from plane 1. Similarly, plane 2 is still connected to all 3 pods, and plane 3 is still connected to all 3 pods. But as we mentioned already twice before, plane 1 is disconnected from pod 1. Positive disaggregation cannot fix this particular type of failure. In positive disaggregation, a node starts advertising a positive disaggregation prefix when it notices that it can reach a prefix that one of its neighbors in the same plane cannot reach. In this particular scenario, that doesn't happen. In plane 1, none of the superspine nodes can reach pod 1, so nobody initiates positive disaggregation. On the other hand, in plane 2 and plane 3, everyone can reach pod 1, so once again, no one initiates positive disaggregation. The first step in negative disaggregation is for plane 1 to discover that it's disconnected from pod 1. In order to achieve that, these top-of-fabric nodes run 2 instances of the shortest path first algorithm. The first instance, or the first run, which is considered the normal run, is used to populate the forwarding tables. In this normal run, the east-west links between the planes are not allowed to be used, and as a result, the superspine nodes in plane 1 will not discover pod 1 and will not install any routes to the leaves or the spines in pod 1 in the forwarding table. If negative disaggregation is used, then the top-of-fabric nodes will also run a second run of the shortest path first algorithm, which is considered the special run. In this special run, the east-west links are allowed to be used. And as a result, plane 1 will discover routes to pod 1, namely routes that go through one of the other planes. These routes to pod 1 are not actually installed in the forwarding plane, but they are used to trigger negative disaggregation. Once the superspine nodes in plane 1 have discovered that they're no longer able to reach pod 1, they will trigger negative disaggregation. They will start advertising negative prefix advertisements, which are indicated by these red arrows, to tell the network that they're no longer able to reach pod 1. They're telling the rest of the network, if you have any traffic to send for any prefix in pod 1, don't send it to me because I have discovered that I'm no longer able to reach pod 1. The show disaggregation command in Rift Python allows you to see the negative disaggregation prefix that a node originates. In this example, you can see that super12 originates negative disaggregation prefixes for each of the prefixes in pod 1. Unlike positive disaggregation, negative disaggregation is transitive in the following sense. When the spine nodes receive a negative disaggregate prefix from each of their parent nodes, they realize that they themselves are also no longer able to reach pod 1. And in that circumstance, they propagate the negative disaggregate prefixes to their children, as indicated by these red arrows. Once again, you can use the show disaggregation command in Rift Python to see both the received and the propagated negative disaggregation prefixes on the spine nodes. When the leaf nodes receive these negative disaggregate prefix advertisements, they use them to install special routes in their routing table with negative next hops. In this particular example, when we look at leaf 2.2, we see a default route that uses all 3 planes to forward the traffic, but then we have specific routes for the destinations in pod 1 that have negative next hops, avoiding sending the traffic through plane 1. You can actually see these negative next hops when you issue the show routes command in Rift Python to look at the routes in the routing table, which is also known as the routing information base, or RIB. Earlier, I mentioned that these negative next hops are a control plane concept only, which doesn't actually exist in the forwarding plane. So just before Rift installs the routes into the forwarding table, it needs to translate the negative next hops into positive next hops. How that happens is explained in this diagram here. Rift looks for the most specific covering aggregate of the negative prefix. Typically, as in this example, it will find the default route. That covering aggregate represents the best path available to the negative prefix. We take the positive next hops of that aggregate and subtract from it the negative next hop of the negative prefix. So we end up with a subset of the next hops of the covering aggregate. Those next hops are installed into the forwarding table, as is shown in the green part of the diagram here. In this diagram, we see the resulting routing table and forwarding table for our example topology. We're looking at the specific prefixes for the leaves in pod 1. In the routing table, or the RIB, we have negative next hops, which indicate that we should avoid sending the traffic through plane 1. In the forwarding table, or the FIB, those negative next hops have been translated into positive next hops, attracting to the traffic to planes 2 and plane 3, which has the net effect of avoiding plane 1. You can use the show forwarding command in Rift Python to look at the forwarding table. For more information on negative disaggregation in Rift, see the blog post or the detailed documentation referenced on this page. The second major enhancement that was introduced to Rift Python since IETF 105 is support for parallel links. Some new keywords have been added to the meta topology file that allows the config generator to generate parallel links in the topology. In this diagram, you can see an example topology that was generated by the config generator with parallel links. In this specific example, we have 4 parallel links on the leaf spine links, 3 parallel links on the spine to superspine links, and 2 parallel links on the east-west interplane links. When you have parallel links into topology, you want to make sure that the traffic is distributed amongst the available links according to the bandwidth available in each link. We'll go through a couple of scenarios to demonstrate how that works. This is the topology that we will be using for our examples. We'll be looking at leaf 1.2, which has 2 parallel links to spine 1.1 and 2 parallel links to spine 1.2. We'll see how leaf 1.2 distributes its traffic across these 4 links in various failure scenarios. Once we start introducing parallel links into the topology, we have to make a distinction between the concept of a neighbor versus the concept of an interface versus the concept of an adjacency. To illustrate that difference, we're looking at the output of the show neighbors command on node spine 1.2 in the topology. Here we can see that that particular spine node has 4 neighbors, but 8 interfaces and correspondingly 8 adjacencies. The reason for that is that we have 2 parallel links to each neighbor, so for every neighbor there are 2 corresponding interfaces and adjacencies. To understand how Rift Python does fabric bandwidth balancing, in other words, to understand how Rift Python distributes its northbound traffic over the available links, we can look at the output of the handy show bandwidth balancing command. On this slide, we have the example output looking at from the perspective of node leaf12. We can see that leaf12 has two neighbors, namely neighbor spine11 and spine12, which you can see in the diagram here and here. From the perspective of leaf12, neighbor spine11 has an ingress bandwidth of 20 gigabits per second. This corresponds to the amount of bandwidth from leaf11 to spine11. Similarly, from the perspective of leaf12, neighbor spine12 has an ingress bandwidth of 20 gigabits per second as well. From the perspective of leaf12, neighbor spine11 has an egress bandwidth of 60 gigabits per second. This corresponds to the total amount of bandwidth that leaves spine11 to any neighbor except back to leaf12. Similarly, from the perspective of leaf12, neighbor spine12 also has an egress bandwidth of 60 gigabits per second. RiftPython distributes the traffic amongst the neighbors in a way that is proportional to the product of the ingress bandwidth and the egress bandwidth of each neighbor. So in this particular example, node leaf11 will end up sending half of the traffic, 50%, to node spine11 and the other half to neighbor spine12. In this example, there are actually multiple parallel interfaces to each neighbor. In that case, the traffic is distributed across the interfaces within a neighbor group according to the bandwidth of each individual link. So in this particular example, each interface ends up with 25% of the traffic. The rules that I have described so far for distributing traffic over the interfaces are actually slightly different from the rules that are described in the Rift specification. But that's okay, because the Rift specification explicitly allows implementation to pick their own rules subject to specific conditions. If we look at the output of the show forwarding command, we can see that the northbound default route actually turns out to be an ECMP route. It distributes all the traffic equally across all 4 available links. RiftPython uses percentages as the next hop weights to make the output easier to read. Now let's look at the first failure scenario. In this failure scenario, one of the links between leaf12 and spine11 has failed. Leaf12 still has 2 neighbors, namely spine11 and spine12. The ingress bandwidth from the perspective of leaf12 into spine11 has been reduced from 20 gigabits to 10 gigabits because of the failed link, whereas the ingress bandwidth into spine12 is still 20 gigabits per second. The egress bandwidth has not changed for either of the spine nodes. As a result of this, spine11 gets 33% of the traffic, 1/3 of the traffic, and spine12 gets the other 2/3 of the traffic. Within the interfaces, each interface gets 1/3 of the traffic. What we end up is once again an ECMP route, but now the traffic is equally divided amongst the 3 remaining interfaces. Now let's look at a more interesting downstream failure scenario. In this example, spine11 has 2 failed uplinks towards the superspines. In this example, leaf11 still has 2 neighbors, namely spine11 and spine12. Both spine11 and spine12 still have the full 20 gigabits per second of ingress bandwidth. However, spine11 has a reduced egress bandwidth of 40 gigabits because 2 of the uplinks have failed, whereas spine12 still has the full 60 gigabits per second egress bandwidth. As a result of this, leaf12 decides to send only 40% of the traffic to spine11 because it has reduced capability to forward the traffic to the rest of the network, and it decides to send 60% of the traffic to spine12, which still has full capacity to send traffic to the rest of the network. Within the link groups of each neighbor, the traffic is distributed equally amongst the links because each link has the same capacity. What we end up with is a non-equal cost multipath route where 20% of the traffic is sent over the links to spine11 and 30% of the traffic is sent over the links to spine12. The last new feature that I'd like to talk about is performance monitoring. which allows you to find out where Rift Python spends its time in its code. What really helps here is that Rift has been specified using formal finite state machines, or FSMs. Most interesting activity in Rift occurs as the result of events being dispatched to finite state machines. We enhanced Rift Python to allow you to keep track of exactly how much time events spent waiting in the queue, waiting to be dispatched to the finite state machine, and once they were dispatched, how long it took to actually process that event. Rift Python also keeps track of various unusual processing times so that you can quickly see if there is a problem. That concludes my update on Rift Python. I'd be happy to take any questions.